Well, welcome to the Randomizer for Friday. It's already the 4th of February, 2022. And I'm your host, Charles Schultz. And we've got some interesting things to share with you tonight. For tonight, our technical term will be fluidic. And fluidic refers to forms of analog or digital computing or processing that is done with either pneumatics or hydraulics or some combination of the two. So we're going to look at fluidic devices and what they're all about. I want to thank all of our supporters, people who've donated and our members and have signed up for our classes, for keeping our channel going and growing. It's been a lot of fun making these broadcasts for everyone, and we hope to continue them for the indefinite future. Thank you to the people who've gone to the page and signed up as members. Please go to schultzlaboratories.com or universesciencecenter.com. Click the buttons to join the randomizer at any time you wish, 6 p.m. weekdays, Eastern Standard Time, or click the button below to get a membership or to sign up for our classes. Every Monday at 9 p.m. Eastern Standard Time, we're running our Meta World series. Lesson 2 will be Monday, and it will be all about developing pragmatic tools. We look at human history and development intellectually from sticks and fire up to nanotechnology. That'll be a great series if you haven't seen any of it before. And the previous episodes will be on the site for people to look at in our little library. Help us to grow and add more material to our galleries and get some people with a lot of technical skills involved with us as well. If you have a specialty or you want to teach it online, get in touch with us. Click the buttons. Join us. So, fluidic. Anybody pretty much knows what a fluid is, but normally when we hear the term fluid, we think of like a liquid. Well, liquids are fluids. Actually, technically, a fluid is anything, a state of matter that will take the shape of its container. So, solids obviously won't do that. Liquids will do it, gases will do it, and actually plasma can do it as well. So, fluids in the traditional sense are liquids or gases. People are familiar with pneumatics, air brakes, suction systems. If you go to the bank and you put the cartridge in the clear tube and it slurps up and goes into the bank, that's a pneumatic system. That's a pretty simple fluid system. Hydraulics, for the most part, most people are more familiar with. The cylinders that operate as the muscles on industrial machinery. Hydraulic systems operate the brakes in your car in most cases. So hydraulics is actually pretty common, and everybody is more or less familiar with it as well. So fluidic, what's so different about fluidics? Well, normally when we talk about logical operations or analog operations, we tend to think of electronic circuitry because that's the easiest way to do it. But before there was electronics, there were many systems that perform logical or digital functions using the flow of fluids. And a perfect example of an everyday use of a system that uses fluid logic is the transmission, the automatic transmission in your vehicle. So what happens in there is it measures the flow or pressure of a stream of fluid, and when it exceeds a certain threshold, it actually switches the gear for you. So as you're speeding up, there is a little valve that's monitoring the flow of hydraulic fluid somewhere in your transmission. And at some critical point, it will act as a switch and it will change gears automatically. And this doesn't matter if you're going up or down in gears, it does it automatically. So that's all done by fluid logic. And digital operations, you're thinking, yeah, I could see an analog operation of fluid flowing and the level changing at a certain rate, yeah. But how do you do a digital operation? So it's actually pretty simple. Imagine you have a cup and there are two entrances to the cup. A stream can flow in the left and a stream can flow in the right. All right, that's pretty simple. Now, at the bottom of the cup, there is a drain. And if fluid flows in one side, it'll go down the drain. If it flows in the other side, it'll go down the drain. But in the center, there's a little cup up in the top. And if and only if two streams of fluid are flowing, they join in the center and drop into the center cup, and it drains. Now this performs a very interesting logic operation. If no fluid is flowing, no fluid exits through that center cup. If one stream is flowing, it misses the cup. If the other stream is flowing, it misses the cup. But if and only if both streams are flowing, They meet in the middle and drop into the cup. This is technically known as an AND gate because it only gives an output if stream A and stream B are both running. So here you can see a simple logical operation. Well, what about the drain at the bottom? If no stream is flowing, nothing comes out. If both streams are flowing, they end up in the middle and they don't come out the drain at the bottom. But if one or the other is flowing, then it will exit at the bottom. That drain at the bottom performs another logical function called XOR, or exclusive OR. So with one device and one or two streams of fluid or no streams, we get two logical functions. Now, the creative can imagine some interesting things you might do with this. So if this reservoir of fluid is filled and some's draining through the one input, you could determine that it was doing so. And if the other reservoir were filled, you could determine if it were. And if both, you'd get a different answer. So this little device can tell you what's happening in those. Doesn't sound like much, but it gives you the basis of the principle of fluidics. And one common logical function is an oscillator. What is an oscillator? Think of it as a sort of a time clock, something that switches on and off regularly. Now, I know a lot of people like gardens, and a lot of people like water gardens, where you have some water flowing over some stones, creating a really nice environment, some greenery growing. And one of the things that I was fascinated with as a kid was in a Japanese garden, and there was a short length of bamboo pipe that was on a pivot. And the water would spill into the pipe, and when the pipe filled, the weight at the top was past the pivot, the pipe would dip over and drain out. And when it was drained, it popped back up again. This is actually a fluid oscillator. And if the flow of your fluid is constant, then it will click and drain at a steady rate with a known period of time. This is the basic principle of a fluid oscillator. Doesn't sound like much, but in most cases, if you need a system that regulates an operation every so often, that's a way of doing it. Here's another fluid logic device. Anytime you flush a toilet and the water drains out of the tank in the back, which technically is acting as a capacitor because it's charged up with water, once the water is down, the float goes down, and what does it do? It opens a valve, and the valve automatically refills the tank. When the float is high enough, the fluid has reached a high enough level to raise the float properly, it pinches off the valve. It closes it. So this is another fluid logic system. You can see that with a little cleverness, you can make all sorts of devices that make fluid control things. And I think that, if you realize it, there are a lot of electronic devices that can do these jobs, but they have a couple of very interesting flaws. Number one, you have to have a source of electrical power for them. And number two, they can blow out. Things can happen to damage them. With fluid systems, for the most part, you just keep it clean, and it'll run forever. Many times in the past, people made fluid devices that did amazing things. And Leonardo da Vinci, who everybody has heard of, Leonardo da Vinci had, call it a contract of sorts, with the leader of the day. And he lived in an apartment and was provided with an allowance and a place to work. And he did his artwork and he fulfilled contracts. And in the meantime, he invented things that his benefactor could use or publish or trade with. Ideas were being bought, in a sense. And one of the things that Da Vinci invented was a type of trip hammer. Now, at that time, wind or water, both fluids, were generally the only power source you had. And so, windmills, and everybody is aware of the Dutch windmills in Holland, were used as power for grinding grain and for pumping water. And Da Vinci knew quite clearly of these things. He designed gears, cages, and escapements that would be driven by mechanical systems. One of the things he devised was a water-driven trip hammer. So what is a trip hammer? In essence, imagine a water wheel turning away and running a gear shaped like a snail shell. And as the gear is running, it's slowly raising a hammer in height until it reaches the discontinuity and the hammer drops. Now, what good is this? Suppose you have to put a lot of posts in the ground and you can set your trip hammer up on a frame over your posts. The flow of water nearby provides the power, and you don't have a bunch of guys up there with sledgehammers beating on the post. The trip hammer can do the job for you. It was an early industrial tool that could provide continuous and regular hammering operations. Well, that was a fluidic device. Now, today, a lot of the things we do are much more subtle than this. So, as you might imagine, we have taken fluid devices, fluidics, and it's evolved quite a bit. If you've ever looked at the interior of a refrigerator or an oven, you may have seen a small copper bulb about 3 or 4 inches long, and this copper bulb has a little thin copper line running off of it. What is that? Many people see it and go, oh, it's just one of those things. Actually, what this is a temperature sensor. And the way it works, as the fluid in that bulb expands, it grows in pressure from being heated. It literally drives pressure down that little thin line to a sensor at the end. And typically it will be a switch with a diaphragm or something like that, so that when you reach a certain amount of pressure, this device is amplifying it. And think about it. If it's in a big thick bucket, it only goes up a little bit, but once you get to the tiny tube, it can move rapidly along the tube. You can see this in a mercury thermometer, the old ones that had the bulb at the bottom and the tube coming up to the top. The expansion of the fluid in the bulb, and this thermometer is a fluidic device, would drive the red alcohol or the mercury up into the graduation so you can read the difference in temperature, for instance. Pressure devices also work in the same way. Well, this little copper bulb is expanding, or the air in it, I should say, is expanding with temperature and driving the thermostat that runs your heater or your oven or a refrigerator. So that's a very simple fluidic device, and it doesn't have any moving parts that you can see, although somewhere it trips a button on a switch or a diaphragm. Today, fluidics has been taken to a whole new layer. Many people have insulin pumps or similar devices implanted in their bodies for their health. And this uses a microfluidic pump. And so basically, they do have a source of power, but often it can be delivered in the form of glucose from the bloodstream or changes in temperature or something simple like that. Microfluidic devices have grown in complexity. Your inkjet printer that has the little dots of ink being squirted out of it has a tiny microfluidic pump about the size of a nickel. And it has a diaphragm on the front and a diaphragm on the back. And this is a piezoelectric oscillator. It's a crystal that electricity makes expand and contract very rapidly. And every time it's pulsed, a tiny droplet of ink is ejected from that pump. So a digital control circuit spits out a series of droplets, and charged plates with electricity steer the droplets through electric charge to draw on the paper. So the droplets can be seen with a high-speed camera to come flying out in a stream. Some are directed down, some stay up, and they all end up directly aimed at the paper to draw the character with microscopic precision. That's pretty amazing. And it might be interesting for you to go on YouTube or something and see if you can find high-speed photography of an inkjet printer. It'll fascinate you. You know, the devices we have built using fluid logic and fluidic devices are amazing. Today, analytical people use these things all the time. There is a device that is literally the size of a microscope slide that contains dozens, if not hundreds, of fluidic devices. You can take a biological sample on the range of a nanogram, 1/1000th of a gram, place it in the system, it'll divide it up into the cells, and it will begin to analyze and give you results. And microfluidics can manage the chemicals going in to perform the tests. The cells each contain a different sample of fluid and a different reagent or chemical mixed with it, that's literally placed on a microscope slide, a stand, or a computer vision system looks at it and analyzes the results. So you can take a flake of skin, a cell, put it in this system, analyze it, and find out all sorts of things in a matter of moments. So fluidics has the potential to become one of the new technologies, and it certainly is going to be involved in the further development of nanotechnology and very subtle things that we can do medically and chemically. So fluidics starts out as being the simple thing of a flow of a liquid or a gas and turns into something truly sophisticated at the other end. So how does this help us? Well, you can imagine in times past having to take a biopsy or a sample of tissue and how invasive it might be. This can be done with an extremely tiny sample today, and the analysis can be done literally in minutes in many cases. So fluidics has brought this sort of refinement of the analytical technology to us in recent years, and it's only going to get better. And eventually you will imagine that as they're manufacturing nano devices, you may have hundreds of types of them being programmed at one shot, and a device like this could provide thousands of little cells for the nano devices to go in and receive their instructions, for instance, under fluidic control. And the bamboo oscillator I mentioned, for most normal mechanical or fluidic devices, the oscillations have to be very rapid because the parts are small and they have to move tiny distances. So one fluid oscillator is literally a wedge of metal and a stream of air blowing over it, and it sings like a whistle at like 5,000 hertz, 5,000 cycles per second. And each of those cycles promotes one operation of the fluidic devices in the system. So fluidics, an amazing concept. Now, if anybody has any ideas, questions, or comments, the floor is open and I will take them. And meanwhile, I'm going to suggest that you go to Schultz Laboratories or Universe Science Center, go to our pages, sign up for a membership, help us out, and become a member and gain the benefits of being a member of the Universe Science Center. Get your Oculus wrist, walk around in there. Your 3D world is waiting for you to explore and have a lot of fun with. And by the way, your support helps us add galleries and content and grow, and including our library, such as this video that you're watching right now. So I do thank everybody who's done that so far. So any questions, we're open for that now. Well, all right. So I would say that that handles the discussion of fluidics, and it's certainly something worth looking up. And I do have a proverb for you tonight, something I really found interesting. Proverbs 12:10, it says, "The righteous care for the needs of their animals, but the kindest acts of the wicked are cruel." Think about that one. It'll come to you pretty quickly. Well, thank you to everybody for listening. And thank you for being supporters. And we hope that you have a wonderful weekend. This is our Friday show. We'll be back Monday with another randomizer, with another technical term. And we hope that you have the best life you can have and do what we all can do to make the world a better place. You know, small things. Put the shopping cart away, pick up a piece of trash. It doesn't take giant things to make the world better. Small acts can do the job. Stick with it. Thank you so much. It's been a wonderful show, and I hope you have a great weekend. Good night.